10 o'clock. I'm going to sort of start right on. I have demos, so I'm hoping we don't go over. If we do, we can always cut stuff out. Not a screen over there. I think, therefore, a pwn. My name's Alex Chaveriat. I go by Silk. Again, sort of what I did yesterday. Some people have called me a hacker. Some people have called me a geek, innovator of the future. And before the end of today, at least 5 of you will call me an ass to my face. Why am I doing this talk? What is it about? I've been to a lot of conferences, and up to this point, I haven't seen one which really goes from I see an application to here's an exploit. So this talk is going to systematically go through the process of we find an application, we test this application, we fuzz the application, we find a bug, we then move it all the way to an exploit, we overcome a few obstacles with that exploit, and really stepping all the way through the steps. If you want to take notes, feel free. I'm sure it will be online later. I'm not going to be able to go into a ton of detail on each step, but the information you get here should be enough where you can go out and do this. Starting off, we're going to be looking at a TFTP application. It actually, I have found it all. This one I have found live during testing. This same application has been tested to death. I am going to be exploiting in a way which I haven't seen. Just being able to jump up the stack a little bit more. It's used for backups. A lot of Cisco routers use it to like back up their running configs. So first, I guess sort of jumping right in, is we need the application to test it. If you're doing a scan, you do an nmap on the system, you find it running something, how do you get it? Well, there's really 2 obvious ways. If you're actually doing this test legitimately where you're actually have access to the company, you can ask for it. It's okay. The second way is really there's application databases online. You can find the version you need. It's really easy to find the version with nmap and whatnot. So first thing, TFTP. We have to learn it before we can pwn it. Before we can start fuzzing, we have to know what in the world it is, how it communicates, really on a very basic level, all the way down. And we look at 2 ways where we can find out how that protocol works. Firstly is looking at the RFC, which is usually a pretty big document. There's a lot of usually different write-ups on it, and it's a huge document. However, we only actually need a few parts of it, one of which is how this communication happens. Is there a preamble? Is there like a handshake that happens? We have to communicate, log in, a connection is made, a tunnel is generated. With TFTP, it's really simple. You send a request to host A sends a request, and our WRQ is a write request, and host B sends back, an ACK. So this is like the perfect application to fuzz because you don't need a handshake. It makes it so easy where you send one packet and then we're off. The next most important part is the packet itself. What does the packet look like? And very simply, there's an operation code, and we can see them up here. 1, 2, 3, 4, data request, acknowledge, an error, a write request. We're going to look at the write request, the file name, a null byte, the mode, and then a null byte. If we want to look more what in the world those modes are, you can do an octet, you can do mail, you can do net ASCII. ASCII. Okay. But there's a bunch of different modes. Again, we have to know what the packet looks like. The next step, and again, what makes it a little bit more clear is when we actually look at it in Wireshark. We can look, this is a write request because the opcode was 2, and again, lining up with the RFC. There's a GrrCON. Let's look at the actual data. Again, and I want you guys to be very specific. There's a null byte which starts it. There's the opcode, the file name, another null byte, the mode, and then another null byte. All this information really ties back to, again, the RFC. And I want this to be abundantly clear how much this has to line up and really how easy it is to understand a protocol on that byte level. So now that we've done that, we can actually start fuzzing. Fuzzing essentially is at probably the basic level is throwing random crap at the thing, intelligent random crap, at the application and see how it reacts. This can be done manually. It can also be done automatically. It can also be done super automatically. Things like Sully and Peach are two applications that do fuzzing, and they can do some incredible automation with them. You could set up VMs which are running the application. It will you can start fuzzing the application. When it registers a crash, it will grab the stack traces, save those to a file, automatically reboot the VM, and then start fuzzing again. Spike is actually included in the Backtrack distro, which is an excellent distro, and it's really simple to use. I'm going to show you how simple it is by us making a template. There is application fuzzing versus protocol fuzzing. Protocol fuzzing is used in a lot of SCADA systems. Application can be everything from web services to you can fuzz a form field, or you can even use intelligent SQL fuzzing, which will just fuzz SQL commands. Live demo. Before I jump into it, I will be trying, if you guys can't see anything I'm doing during the live demo, tell me. I can zoom in and show it a little bit more clear. I know with these big screens, sometimes you can't see it as much. So we're doing it live. I know live demos can get a little monotonous, so I'm going to try and show it in a way, but I really want you guys to watch systematically how we go about this, really. What we want to do is we're going to start up the application, and we're going to start up our debugger. I use Ollie. It works great. We search for the executable. And as you can see it right in there with the process ID. Attach it, run it. We are now running our application inside our debugger. At this point, we want to load up our fuzzing template. We know it's a UDP packet, so 1 second. Just so I don't lose my spot here. Now you guys see that a little bit more. We put in our IP address, which is running the server, the port, and the template. Let me zoom out here so I can show this to you. I know I showed this up on the screen. I wanted you to see this is exactly what the template looks like that Spike uses. Again, our null byte, the mode, the file name, a null byte, the mode, or sorry, the file name, the mode, a null byte, and sleep usually makes it a little bit more stable just because it's going to wait, a hair of a second before it sends the next request. That's just 1 millisecond. Within Spike, you can set, again, binary strings, what's the actual hex byte, which is going across the wire, and then string variables. We saw file.text and netASCII go as the mode in the Wireshark capture, and you can specify them here. Setting underscore variable will fuzz that parameter, and Spike has within its testing set, it has about 5,000 tests it does per protocol. So we want to start testing variable 1, which is 0, which is the file name. We're going to start at test 0, and we'll go up to 5,000. So I'm going to kick this off and go on over to our other screen and watch this. And if you notice, immediately the application pauses. We can go ahead and cancel this. Looks like that was the one that caused it. And we notice something really interesting. It's not going to be a straight EIP overwrite. However, we did get a couple registers to actually collapse on us or overwrite. Looks like our buffer is stored in ECX. We can follow our stack pointer. And the biggest thing we want to look at is the SEH chain. And we notice that 41414141, which is an overwrite. Spike sent a big buffer of A's, and we can capture that in Wireshark, and it overwrote this SEH handler. Now, without going into a lot of detail, essentially, these exception handlers work within Windows. If an error happens, it hands it off to this exception handler. If it's broken, it will keep jumping up. It will keep jumping up those exceptions, so the operating system doesn't just crumble when one application crashes. So it's an intelligent way of handling those errors. So what I was able to, again, what we're able to do now is we want to reduplicate this in a Python script or whatever your script is, so we can understand and reduplicate it and give us something to move on from. So this is essentially, can you guys see that all right? Awesome. Well, that wasn't helpful at all. I'm going to see if I can make this a little bit better to see really fast. Oh, black. That's what I meant to do. There we go. A little bit better? You guys see it now? Awesome. Again, this is Python. It creates a socket. We set the host port. Essentially, this is the information we're interested in. We want to reduplicate exactly what we're seeing not only in Spike, but also in what Wireshark to recreate that packet format within something we can edit. We know, looking at Spike, and I'll jump back on over to that. I actually ran it in this window. That it was about 5,000 bytes within the file name, which caused that crash to happen. So essentially, we just recreate that within Python. We set up our null byte, our write mode, the file name, and then net ASCII just to throw it in the mode, followed by a null byte. So just to make sure we have this right, let's run it again and reduplicate the crash. We attach our debugger. It's running. Run it. We get the exact same crash. So if we want to hijack this handler, we have 5,000 A's, 41 in hexes A. We have to figure out where in the world that is. How can we do this fast and efficient? There's really two ways of doing it. We can either, with a 5,000 byte buffer, we can separate it and go 2,500 A's, 2,500 B's, and then keep cutting it in half, and it'll take 7 or 8 times maybe to get something where we can understand it. Metasploit, the Metasploit framework, is a really cool tool which allows us to find this a lot faster. Essentially, it comes up with a systematic range of, I guess, numbers and letters, which then you can search and find the exact position. So we're going to generate one of those. It's called pattern create. It's under the tools directory. And we want to create one which is 5,000 bytes long. And you can see it comes up with this big, ridiculous string. So you don't have to watch me type it in. I already added it. So essentially all we're doing is we're taking that same one and we're putting it in our file name. I'm hoping this text works a little bit better. And then we get to run this. Unfortunately, with this application, you can't just restart it inside the debugger. You actually have to open it up and reattach it. So we now reattached it. We'll run that exact same exploit. We got our crash. And we have this really weird looking string now in the set handler. What's cool about this, and again, I'll zoom in so you can see it. What's really cool about Metasploit in this tool is I can go ahead and copy the clipboard. Go back to that same pattern creator and look at the offset. Grab this offset that we found, copy it in the string, and it will tell us the exact byte, which leads to us hijacking that handler. So 1,496 bytes, and we're going to hit that handler right in the nose. We're going to do a quick test of this because we want to make sure we're accurate. And once we set this, we don't want to deviate from that 5,000 because we know we're going to be able to control our crash that way. We reattach it. We put our number in here, 1,496. We follow it by 4 B's, and then 3,764, which is just, whatever's left of C's. We send it. We cause the same crash. We want to make sure we were accurate, and we were dead on. 4 bytes, exactly where we want them. We can even actually follow that in the stack. And see exactly where we overwrote that. So let's close this down. Let's take the next step. Attach it, we run it. So at this point, we have that in the stack. We have control of our set exception handler. We know that our buffer is above that, and we know exactly, let me pull this up. This is the one we just sent. We know that we hit the set exception handler right at the B's. We know we have this wonderful space up here. But how the set exception handler works, or the stack exception handler works, we need a pop ret. We need to pop 2 spots off the stack so we can actually get to executable code. In order to do that, again, Metasploit is a great framework to use for exploitation. We can just scan for a pop ret in the executable or the running DLLs. There's one problem within Windows. Besides the many, there's one thing which actually really prevents us using set exception handlers sort of against them and being able to use set exception handlers from other DLLs, and that's safe SEH. There's a great module for Ollie which allows you to search DLLs that are loaded, which are needed for this executable. So all of these are loaded. The problem is, when this operating system was created, every single one of them was created with that flag on when it was compiled, so we can't use them. However, sort of good is that the actual server executable, it's not compiled with it. However, there's a sucky problem I ran into in exploiting this. Anyone see what it is? It has to do with a null byte. The entire range that's loaded in has a null byte in it. It has 2 zeros next to each other, which, when judging by the RFC, when that's ran through the application, it will expect the next part. It will expect either a mode or a file name when it hits that null byte. So we need to figure out a way around that. Right now, we'll just put it on hold. First, we need to find a pop ret. So again, we can use PE scan. Search the executable, and boom, there's a ton of them. We can grab any one of these. Usually we don't really care what it's popping off the stack. We just need it to pop 2 things off the stack. So we grabbed one. I just grabbed this one right here. We can run this if you want. Essentially what we want is we want redirection to go down, redirection, which we hijack in the SEH handler, and jump over to our pop ret. Let's run this one really fast, and we should be able to start understanding, how we're going to circumvent some of the security and get our payload in there. Restart the application. Attach your debugger. Run it. We catch our crash. If we look, I'd set a breakpoint. We overwrote it with our pop ret. I'm going to go ahead and pass this exception, and you go Shift F9. We then jump within execution back to the pop ret. Now let's see how this works and show it in the stack. We run the first pop, and it pops the first one off the stack. You see down here? We'll run the next one. It pops the next one off the stack. And we return to our original operation. In here, awesome. This is not always the best feeling when you only have 4 bytes to fit in like a 300-byte exploit. So we now have to figure out how in the world we're going to get out of this. Anyone have an idea? Well, we have all this space up here from our original exploit. Let's use some of that. From this, what we can do is let's just jump up the stack a little bit. Now we ran into that null byte earlier, which I did want to come back to. This will not be able to get passed because it has this null byte in it right here. What will happen is when it gets passed over the wire like this, the application will go, what's going on? Because it will see our file name, this null byte, as in the RFC, this null byte, and then it will hit the mode. And it won't actually create a packet which the application can use. So what we can do is we can actually leverage its own protocol against itself. The way we do this, and maybe this will make it a little bit more clear, is we can use the null byte which the RFC uses or TFTP uses in its protocol to overwrite that last byte. So instead of passing it here, we can pass it right after the file name and leverage the protocol. And we can get the jump we want. So we have exploited it, or we hijack the set handler. We have our pop-up ret, and now we're stuck with like 4 bytes or 4 bytes that we can't do any. There's no space for our exploit. So I mentioned, let's jump up the stack. We can do this with the simple short jump command. Right there, and we can just fill the other 2 spots with nops. We run this, we catch our exception, we pass it, we hit our pop ret. We are now at our short jump, and we jumped approximately 128 bytes up the stack. Awesome. We have like 128 bytes to fit something in. At this point, we could do like an egg hunter. An egg hunter essentially will search the memory frame and look for your payload. Cool, but not nearly as cool as not wasting memory and space and making it really obvious to the end user, their CPU spiked to 100. We still have a ton of space up here, which we can use. We just have to figure out a way of jumping to it. Now, we can systematically try and jump up or hijack it, but what's great about exploitation is that a lot of people have done it, and people who can waste a lot more time than me. Aaron Adams came up with an excellent way of controlling the stack and making those large jumps. And here it is. He originally wrote it in FRAC Article 62, or Issue 62, Article 7. And it allows us to jump approximately 512 bytes up the stack. And he essentially does this by popping ECX off the stack. We can add to it, and then we decrement it twice, and then we just jump right to it. So let's compile that. We have it right here. Copy that. And we now have that in our application right here. At this point, and again, something really important we want to know is we want to keep this number extremely consistent throughout, because if that moves, everything moves with it. Our stack exception handler, everything goes along with it, where we're not going to line up how we want. So we want to make sure we keep all of our numbers very consistent. So we're going to throw in, I'm just throwing in a bunch of breaks in there, a bunch of CPU interrupts. We throw in nops. We throw in our longer jump back. At this point, we're going to then do our stage 1, which is going to do our short jump back. It's then going to execute this, which will be our stage 2, which will then jump back a little further. We're going to go ahead and load that one up. Restart the application. Open our debugger. Attach it, run our skeleton code, pass the exception. We hit our pop ret. Zoom in a little bit. Pop, return. We hit our short jump. We're back 128 bytes. We hit our NOP sled. We now hit Aaron Adams code, which you can see in the registers. Decrements twice. We then get ready for our jump. And now we have about 512 bytes to work with, which is awesome. We hit stage 1, we hit stage 2. Now we have a ton of space. So great, we have space for our exploit code. We can now just generate one and hope not to run into any more problems. Get that running, jump on over. So I don't have to type it out. I'm going to just generate a reverse shell. We want to make sure we grab one which is going to encode it actually with no null bytes. Pass it to encode, get rid of the null bytes, drop that in our next one. This will take a second to generate. So at this point, we're passing it. We have enough space to throw it in. Highlight our payload. We drop it in right here. We make sure we have all of the spacing right. I just used a quick length measurement within Python just so I didn't have to keep calculating it. Because without fail, every time either the payload doesn't work, something, we might get a weird encoding format. So that size might change. So to keep our NOP sled the same, we load our shell code. We have our long jump back. Save it. We're running. We're going to come across one last hurdle. Pass the exception. Pop ret. First jump. Second jump, we hit our NOP sled, set up a listener on this side. We'll let it run, and we get an access violation. What sucked about this is I had to go through the payload one byte at a time. There is easier ways of doing it, and I came across a formatting error within the exploit which the application can't handle. This byte right here, 2F, actually within the RFC, if I would have paid attention, doesn't allow backslashes within the protocol. If it does, it registers like a debugging command within TFTP, which isn't allowed. So how do we get around this? We regenerate our same payload. We pass it to an encoder. With 2F saying we don't want that. reload it in so we no longer have a slash in it, or forward slash in it. Launch our debugger one more time. Within all exploitation, there's always back and forth, and I haven't come across one which has been straightforward. Usually there's always some jump or encoding that you have to get around. Run our application, check our exploit. Have our listener set up, launch it. The breakpoint hits, we pass our exception, we hit the pop ret, we do our short jump back, Aaron Adams long jump, we're now in our NOP sled, we let it run. To make it nice and visual, let's close that. Bring this over, eventually. We will run it. Launch the application. This point, launch our final exploit in gain shell. We now have access to the application. In the back end, we hit our bind shell. We can get access to files and access to the machine. Cool? Thanks, guys. Again, I know sometimes live demos are very monotonous and going through them. I wanted to show the complete steps through it, overcoming, again, obstacles like jumping, not having enough shell code. There's always a way. Again, if you can get around that, usually there's always a way. You just have to keep working at it. Thanks, guys. Thanks for coming to my talk.